All right, hi everyone. My name is Gemma Cremen. I'm from UCL, and I'm going to do this presentation in collaboration with my colleague, Professor Carmina Galasso at UCL, but many other people have contributed to the various research I'm going to show, and I'll mention their names along the way. So before we get into the research that we actually did in this topic, I just want to first go through what exactly earthquake early warning is. So we have an earthquake and we have a rupture. And the first type of waves that emanate from an earthquake rupture are P waves. And in an earthquake early warning system, what we'll have is we'll have a series of seismic sensors located in areas that are likely to be close to epicenters. And these seismic sensors detect the incoming P waves, and then a series of algorithms are used to take the P wave information and translate that information into predicted characteristics about the ongoing earthquake, such as its location, its magnitude, and then in turn, we can use, for instance, ground motion models to determine the predicted ground shaking intensity associated with the incoming earthquake in space. So this is what we would call a network or a regional earthquake early warning system. We can also have an on-site or single earthquake early warning system where we just have one sensor located close to a particular structure or critical infrastructure of interest. Then a series of algorithms translate the P wave information, in this case, directly into ground shaking information at the site of interest. And then for any type of earthquake early warning system, the last step in the process involves making a decision. So based on the predicted characteristics of the incoming earthquake, should we issue an alert or not, so that people can take protective measures before the stronger S waves from the earthquake actually hit their location. So in summary, earthquake early warning consists of both hardware in the form of seismic sensors, as well as models, methods, and algorithms for translating early P wave information into characteristics about the oncoming earthquake. So if an earthquake early warning is issued, the time between when the alert is issued and when the actual shaking from the earthquake hits people is on the order of seconds to tens of seconds. So we can take some rapid actions to mitigate the risks associated with the incoming earthquake. For example, we can duck, cover, and hold to protect ourselves from injury. We can slow down trains. We can prevent cars from entering bridges. And we can even evacuate, say, the ground floor of buildings if we have sufficient time. So I did a review on earthquake early warning systems back in 2020, and what I found from that was there was about 9 operating earthquake early warning systems across the world and 13 more in testing. Of course, this has been updated in between. For example, Israel now has an operational system in place. So we've got various organizations around the world in charge of earthquake early warning systems. We've got the USGS, for example, rolling out the Shake Alert system on the west coast of the US. We've, of course, got the TURNkey project rolling out earthquake early warning and testing earthquake early warning for Europe. And then, for example, we've got the Japan Meteorological Agency in charge of earthquake early warning in Japan. So let's move on then to the first part of our research, which looked at investigating the potential effectiveness or feasibility of earthquake early warning in Europe. Now, for this particular study, we focused on kind of the first step involved in an earthquake early warning system, which is detecting the incoming P waves using seismic sensors. So the first thing that we did was we identified high hazard area sources across Europe. So these are area sources where the earthquake with a recurrence interval of 500 years was at least a magnitude 6.5. So we did this to identify areas that would most benefit from the risk mitigating beneficial effects of an earthquake early warning system. We then combined this with velocity models to determine how quickly P waves and S waves would emit from these particular area sources. And then the final step involved determining where seismic sensors are located across Europe in relation to these high hazard area sources. We can combine all of this information together, and what we produced was a lead time map for target sites that are affected by these high hazard area sources. Now, what the lead time map tells us is basically the amount of time people would have to take risk mitigation effects if an earthquake early warning system was in place and an alert was issued. So the more lead time a target site has, the more beneficial an earthquake early warning system would be for that target site. But this here, what I'm showing, is just one lead time map. In reality, any target site will be affected by a number of different high hazard area sources, each of which will have its own lead time for the target site. So each target site actually has a distribution of lead times associated with it. And we determined that distribution for each of the target sites to come up with various different lead time maps. So we can have a minimum lead time map, which is the worst case scenario, the least amount of time a given target site would have to react for an incoming earthquake. We also have a median lead time map, as well as a best case scenario, a maximum lead time map. So what we found from this study was around half of the target sites that we looked at would benefit from at least 5 seconds of lead time in a best case scenario. Now that 5 seconds could be used to duck, cover and hold. It may even be used to evacuate ground floor of buildings, for example. So this was a very positive indicator of the potential beneficial impact of earthquake early warning in Europe. But lead time isn't the whole story, okay? So what we did was we combined the lead time map with information on where people live in relation to the amount of lead time that's available, as well as the type or the intensity of shaking that they might experience in these earthquakes, to come up with a more informed idea of the beneficial impacts of earthquake early warning in Europe. And if we combine all of this information together, we can come up with plots like this, where we have examined population on the y-axis, different lead time maps on the x-axis, and then the different plots correspond to seismic intensities that the population might be exposed to from incoming earthquakes. So if we add up both axes of these plots here, we find that about 98% of the examined population are exposed to seismic intensities between strong and damaging. So this means that earthquake early warning could have a significant impact on earthquake risk. And then the next thing to note is that if we look at the maximum lead time map bar in particular on the right-hand side of both plots, it's well colored, which means that a lot of the population has at least some lead time in a best case scenario to protect themselves from these high intensities. So again, we're getting a positive indicator of the potential beneficial impacts of earthquake early warning in Europe. We then went one step further and synthesized all of this information into a more formal metric, which we called a relative feasibility index. Now, this relative feasibility index accounts at each target site for the population around that target site, the median lead time that target site has for incoming earthquakes, as well as the average seismic intensity that might hit that target site. And it's relative, which means we're ranking different target sites relative to each other. So the best target site and the target site with the highest relative feasibility index would be one that had the highest median lead time, the highest amount of population around it, and the highest average seismic intensity. Now, what we also introduced in this type of metric is weightings on each of the different components. And this was to account for diverse stakeholder preferences towards the underlying components, because we might imagine that maybe one stakeholder is more interested in installing earthquake early warning in an area where there's a high amount of population, whereas another stakeholder might prioritize the installation of earthquake early warning where we have enough lead time. So in the next plot, we're going to assume that the relative feasibility index and its different components are equally weighted by the stakeholder. Now we calculate this relative feasibility index for each of the different target sites, and we find that the most feasible sites for earthquake early warning are located in Italy, Turkey and Greece, supporting TURNkey's installation and focus on earthquake early warning in both Italy and Greece. Now, what we'll conclude from this part of the study is that about half of the target sites that we examined would benefit from at least 5 seconds in a best case scenario. Now, this points to the potential beneficial impacts of earthquake early warning. But as a supplemental tool to other measures, it's important to remember that earthquake early warning isn't a cure-all solution. We also need, for example, good building codes in our areas. But within a suite of different risk mitigation products, earthquake early warning could be particularly beneficial for Europe. And then, as we saw on the previous slide, the most feasible areas for earthquake early warning are Italy, Turkey, and Greece. So I carried out this study with Cremen and Elisa Zoccolo at EUC, and we were lucky enough for our study to be published in Nature Communications, and there was a number of recent media articles about the study, and it was great to see that our study had impact across the world. Now, moving on to the second part of the research that I'm going to focus on, which is accuracy and uncertainty of the underlying algorithms in an earthquake early warning system. So how good are they at taking P-wave information and translating that into accurate characteristics about the incoming earthquake? So I'm just going to briefly go through this study. What we did was we compared two very popular earthquake early warning algorithms, the PRESTO algorithm and the virtual seismologist algorithm, taking earthquakes and synthetic events that have been recorded or simulated at 4 different TURNkey testbeds. And what we did was we examined accuracy and uncertainty. And what I mean by accuracy is how accurate were its magnitude and its location predictions of each of the algorithms relative to the true magnitude and the true location of these different earthquakes, and also accounting for the uncertainties that underlie these predictions, because any algorithm will predict something, but it will predict something with some underlying uncertainty incorporated. So what we did was we took the predictions of both algorithms, accounting for their accuracy, but also the underlying uncertainty, and translated that into a ground shaking distribution, and compared the ground shaking distribution of the algorithm's predictions with what actually would have occurred if we had the true magnitude and the true location of the events. We summarized all of this into a metric called the MD metric, and we compared both algorithms. And what we found was that both algorithms perform pretty well when we have smaller uncertainty on the underlying parameters of the earthquake, but then PRESTO performs superiorly if we have higher uncertainty on the underlying characteristics of the algorithms. And that means that earlier on in an earthquake early warning process, there tends to be more uncertainty on the underlying characteristics. So PRESTO is better if we want a more timely prediction and we want more time in order to take risk mitigation actions, whereas if we have more time to wait, virtual seismologist also becomes a good selection. So we did this study in a both theoretical sense and also an operational sense, kind of taking all of the predictions and looking at them as if they happened in pseudo real time using the real operational systems of both algorithms, and we found consistent results for both types of approaches. Again, I carried out this work with Cremen and Elisa. So let's move on then to the third part of the research that I want to focus on in this presentation, which is looking at the decision module of an earthquake early warning system. Now, in conventional earthquake early warning systems, what we tend to do is we tend to make a decision on whether or not to issue an earthquake early warning alert purely on the basis of seismological characteristics of the incoming earthquake. So if its magnitude is predicted to be large, or the ground shaking at a particular location is predicted to be large, we then decide whether or not to issue an alert. But this isn't the best way of making a decision on whether or not an earthquake early warning alert should be issued, because it doesn't properly take into account the impacts of that earthquake on the built environment and on society. For that type of analysis, we do also need to incorporate some earthquake engineering methods and tools. The second limitation of conventional earthquake early warning decision-making approaches is that they fail to consider the stakeholder. What is the stakeholder prioritizing in terms of their decision-making? And if we can engage the stakeholder, maybe we could encourage wider adoption of earthquake early warning in general. So we address these two limitations of conventional decision-making for earthquake early warning by developing a methodology that incorporates earthquake engineering tools in the form of seismic performance assessment procedures and multi-criteria decision-making tools to incorporate stakeholder input. So in terms of these seismic performance assessment procedures, one example would be the FEMA P58 procedure. I'm not going to get into the details of this procedure here, but the idea is that this type of method will take ground shaking input and will translate that ground shaking input into interpretable impacts of the ground shaking on the built environment in terms of repair costs, repair time, and casualties for more informed decision making on whether or not an alert should be issued. Then in terms of multi-criteria decision making, this requires active engagement and input from the stakeholder. They need to tell us what criteria they are using to make a decision on earthquake early warning, how important each of the criteria are to them, and finally, they need to provide some input for some of these different criteria. So this last description might seem a bit abstract, so let's go through a bit of a description and an example case study. So let's assume we want to install earthquake early warning in a school. Now in this case, the stakeholder might be the headmaster of the school, and their criteria might be, okay, I want to maximize safety, I want to minimize school disruption, and I want to maximize public satisfaction. So the first part of our method involves taking each of these criterion and translating them into a quantitative indicator. So we can think of maximizing safety as minimizing casualties, minimizing school disruption by minimizing the number of downtime days, and maximizing public satisfaction as minimizing disruption, but also minimizing repair costs or costs associated with a given action. And if you remember from a previous slide, we can actually quantify casualties, repair costs, and repair times using a seismic performance assessment procedure. But really what happens is it's the values associated with each of these different criteria or consequences, as well as the importance of the consequences to the stakeholder, that will determine if a given risk mitigation action is taken for an incoming earthquake, including, of course, the possibility of not taking any action at all. So what we do is we summarize the criteria in what we call a consequence matrix, where each column of the consequence matrix corresponds to a particular criterion, and then each row gives the value of that consequence or criterion for a given risk mitigation action. Now, some of the information in this table comes from the stakeholder. They need to tell us how disruptive a false alert would be. So if we unnecessarily took a risk mitigation action, what kind of consequences are associated with that scenario? So in a school case, for example, we could imagine that a false alert would lead to unnecessary panic and disruption in the school day. Then some of the information in the matrix will come from both the stakeholder and our earthquake engineering procedures. And this is related to the risk that is left over if we take a given risk mitigation action. So even if we take a risk mitigation action in an earthquake early warning situation, not all of the losses associated with the incoming earthquake will actually be reduced. We might have some residual casualties or repair costs, for instance, and we need to understand that in our decision-making process. Then the last piece of the puzzle is the consequences associated with taking no action at all. And we can get this information directly from our earthquake engineering procedures, because if we don't take any risk mitigation action for an incoming earthquake, then all we're doing is simply a conventional seismic risk or loss assessment for that earthquake. So once we have our consequence matrix, the next step is to translate that into a decision matrix, where each of the entries in the decision matrix are simply the consequence matrix, but normalized and also weighted by the importance that the stakeholder places on each of the different criteria. Then the last step involves taking the action or no action that collectively minimizes the values of the decision matrix. So we have a consequence matrix that can translate it into a decision matrix to determine the optimal action. Now, the consequence matrix relies on seismological information from an earthquake early warning system, similar to a conventional approach. However, in our advancement is that we then combine that seismological information with earthquake engineering procedures to convert it into potential impacts of the incoming earthquake on the built environment for more informed decision making. The last step involves stakeholder input in the consequence matrix, but also in the decision matrix to tell us how important each of the criterion are to them in their decision-making process. So let's go through some quick examples of this method. Let's first focus on a hypothetical school. Now, in this case, we're just going to assume that there are two possible actions. We either issue the alarm or we don't issue the alarm, and the criteria are the same as what was discussed in the previous slide. So we're going to go through our methodology, but here we're going to assume an idealistic scenario where the earthquake early warning system is providing us accurate ground shaking estimates. So we can go through this methodology for a number of different potential earthquakes experienced by the school and a number of different ground shaking estimates experienced by the school to come up with a plot that looks like this. So here we have our optimal action on the y-axis as a function of ground shaking on the x-axis, and we're showing the optimal action for different stakeholder preferences towards the underlying criteria. Now, the first thing that we can understand if we combine this type of analysis with seismic hazard information for the site is how often is the alarm triggered. But I think the most important thing to take away from this plot is that the optimal action for a given level of ground shaking can change depending on stakeholder preferences towards the underlying criteria. So in this case, if a stakeholder prioritizes minimizing casualties, they'll end up triggering an earthquake early warning risk mitigation action at a much lower level of shaking than they would if they simply minimized downtime. So stakeholder preferences are key in this decision-making process. So let's move on then to a final application, which is the port of Giotaro in southern Italy, a turnkey testbed. Here we're not just dealing with a building, but we're dealing with a complex interdependent system of components. Now in this case, we're again going to assume there's just two possible actions, but we're going to replace some of the criteria with a new criterion called port performance loss, which basically tells us how much less productive the port is as a result of taking a particular risk mitigation action. So what we do in this case is we assume again an idealistic scenario where the earthquake early warning system is providing us accurate estimates of ground shaking intensity, and we examine the optimal action for a number of different cases. So some of these cases correspond to different stakeholder preferences towards the underlying criteria. But remember in this case that we're dealing with a complex system of interdependent components. So what we also introduced here was different levels of assumptions on the interdependent functionality of the underlying components. So in cases 4 and cases 5, what we're actually doing is we're simplifying the system and its interdependent functionality. And what we find is that if we simplify our assumptions, we end up with an unconservative result. So we end up triggering the alarm at a higher level of ground shaking than we should. And again, what we can see from this plot is that stakeholder preferences and priorities are important in the decision-making process. So in conclusion, we've developed this methodology that integrates earthquake engineering related procedures with multi-criteria decision-making tools. We found that the optimal action can of course change depending on the shaking intensity associated with the incoming earthquake, but more importantly, stakeholder preferences towards the underlying criteria, as well as the assumptions that we make in an interdependent complex system scenario. It's important to remember, that this type of plot that I showed on the previous slide, we can actually prepare this plot ahead of time before any earthquake happens, and then simply consult this plot in real time once we have some estimates of the ground shaking intensity associated with the incoming earthquake. So it's still very efficient decision making. And finally, I just want to mention that I carried out some of this research with Francesca Bozzoni at EUC, as well as Silvia Pastorio and Carmine again. So here are just some additional references, some related to some of the research that I showed. We also have some research that I didn't manage to show, but here are some of the references in case you're interested. Thanks very much for listening.